Okay, so hello and welcome back. So in this video we want to talk about binary operations, and so let's go through the text and see what we have here. So binary operations. So what these binary operations are, we have right from the school days you must have come across 4 fundamental operations. So we have had basically all of these 4 fundamental operations, which were basically addition, namely addition. Then we had subtraction, we had multiplication, and division. So we had these 4 fundamental operations as addition, subtraction, multiplication, and division, right? So the main feature of these operations is that any 2 numbers a and b so the main feature of these operations is that of these operations is that basically given any 2 numbers a and b, any 2 numbers a and b, we associate another number another number a plus b, or basically a minus b, or a times b, or a divided by b, where b is not equal to 0. Now it is to be noted that only 2 numbers can be added or multiplied at a time. So you know that basically only 2 numbers can be added or multiplied at a time. So when we need to add 3 numbers, we first add 2 numbers and then the result is added to the 3rd number. Thus addition, multiplication, subtraction, and division are examples of binary operations. You can say that thus addition, you can say that thus addition, multiplication, subtraction, and division and division are examples of binary operations. Are examples of binary operations, and the word binary means two, meaning that basically this operation can be done on two numbers, or two, they call it two operands, I suppose. If I take a look at the word operand, so basically an operand is basically, what it means is that an operand is the quantity on which an operation is to be done, right? So that means that these operations, basically addition, multiplication, subtraction, and division, are binary, and they have two operands, only two, not more than two operands. Meaning that basically if there are more than two operands, then first you have to take care of the first two operands, and then the third operand will be, for example, added to the result of the addition of the first two operands, basically. So that is that. Now, if we want to have a general definition which can cover all these four operations, then the set of numbers is to be replaced by an arbitrary set X, and the general binary operation is nothing but association of any pair of elements A or B from the set X to another element of the set X. This gives rise to a general definition as follows. Now, what they have jumped a little bit forward in the text in this part, but let's see if we can make sense of what they have written. So they have written that if we want to have a general definition of which can cover all these four operations. All these operations. Then the set of numbers. Now, I don't really understand what is meant by the set of numbers, but I suppose the set of numbers is basically, since we said that basically addition, multiplication, subtraction, and division are examples of binary operations, that means that basically you take those operands from a set of numbers, from two sets of numbers. Those two sets of numbers could be the same set, right? So then I can assume that what they mean is that the set of numbers is basically, what they mean by the set of numbers is basically the set of numbers from which A and B, or the two operands, are taken. And so the set of numbers is to be replaced by an arbitrary set X. So you can say that the set of numbers is to be replaced by an arbitrary set by an arbitrary set X. And then general binary operation is nothing but association, and then general binary operation is nothing but association of any pair of elements A comma B from X to another element of X. Now this gives rise to a general definition as follows. Okay, so definition number 10 is basically a binary operation star, for example, a binary operation star on a set A. Set A is a function star which goes from the Cartesian product of A and A to A, and we denote star of A comma B by basically the star of A comma B we denote it by A star B, right? So as an example, example number 29, we have show that addition, subtraction, multiplication are binary operations on R, but division is not a binary operation on R. Show that addition, subtraction, and multiplication are, so we want to show that addition, subtraction, and multiplication are binary operations. Binary operations on R, but division is not a binary operation on R. So further show that that division is a binary operation on the set further show that division is a binary operation on the set R star, which is basically of non-zero real numbers. Of non-zero real numbers. Okay, so now as the solution, we have, so basically we said that by the definition, we said that the definition was that a binary operation star on a set A is a function basically star on the Cartesian product of A and A to A basically. And then basically the star of A comma B, and A comma B is basically a member of this set, which is the Cartesian product of A and A. So basically the star of A comma B, we denoted by A times B, or not A times B, but I'm sorry, A star B. Okay. So then by this definition, you can say that now I want to show that basically addition is a binary operation on R. So then I can write addition as a function from R, the Cartesian product of R and R to R is given by A comma B to A plus B. A comma B to A plus B. And now I need to familiarize myself with the notation here. Let's go with this. Let's see where this is taking us. Now basically subtraction R, the Cartesian product of R and R to R is given by A comma B to basically A minus B. And then we have multiplication, which is the Cartesian product of R and R to R is given by A comma B to A minus, to A times B. Now we can say that since addition, subtraction, and multiplication are functions, they are binary operations on R. But division from basically the Cartesian product of R and R to R given by given by a comma b to a divided by b is not a function and hence not a binary operation. Is not a function and hence not a binary operation, and hence not a binary operation as for b is equal to 0. As for b is equal to 0, a divided by b is not defined. Right? So what that means is that now for all of these operations, addition, subtraction, and multiplication, we have no problem. For example, for basically you can take any member of this set R, the Cartesian product of R and R, and any a comma b, and add them together, and a plus b is still going to be a real number. If you subtract, the same thing is going to happen. If you multiply, the same thing is going to happen. R a minus b is still going to be a real number, and a times b is going to be a real number. The only way that you will get into problems is that is when you divide, and when you divide, basically a divided by b and b is equal to 0, in which case a divided by b is not defined. It doesn't belong to the set of real numbers, so then this would not be a function, right? But then of course you can argue that however division as a function from basically the Cartesian product of R and R into R, given by into basically R, it has to be of course R star and R star, given by basically a comma b to basically a divided by b is a function and hence a binary operation on R. And the reason why that is a function is that of course 0 is not present here, so you cannot divide by 0 in the first place. Okay, so the next example that we have here is example 30. Is example 30, and that is show that subtraction and division are not binary operations on n. Show that subtraction and division are not binary operations on n. So when we say that subtraction and division, for example, are or are not binary operations on n, So again, what that means is that, for example, so a binary operation star on a set A is a function, basically is a function star from the Cartesian product of A and A to A, right? And so what that means is that when I say that, for example, subtraction is not a binary operation on n, suppose that I say that subtraction is not a binary operation on n, right? So what that means is that subtraction is not a binary operation on n. What that means is that the binary operation star on a set A is defined as simply as this thing, meaning that star as a function star from basically the Cartesian product of A and A to A. And what that means is that now subtraction, we want to say that it's not a binary operation on n. That means that I write subtraction here as a function, and it goes from the Cartesian product of n and n to n, right? So if this is true, then I can say that subtraction is a binary operation on n. If it's not true, then this statement is true, right? Now we need to now you can, for example, you know that the Cartesian product of n and n could be, for example, some ordered set. The Cartesian product of n and n would be all of these would simply be a set, would simply be basically the set n here and the set n here, and you have all of these relations from every element from the first set to every element to the second set. And then relative to that, so for example, you have 1, 2, 3 all the way up to infinity, and 1, 2, 3 all the way up to infinity. That means that there is a relation from 1 to 1, 1 to 2, 1 to 3, and so on and so forth. Again, you have a relation from 2 to 1, 2 to 2, and 2 to 3, and so on and so forth. You have a relation from 3 to 1, you have a relation from 3 to 2, 3 to 3, and so on and so forth, and so on and so forth. So this just keeps going forever. So which means that, for example, and these relations will be represented by the Cartesian product of n and n would be a set of ordered pairs a comma b in such a way that a belongs to n and b belongs to n, meaning that a comes from the first set here, which is, well, in function notation you can call it domain and codomain, but these are really no domains and codomains because this is not a function in the first place. But then the first element comes from n and the second element comes from n again, and they are of course the same sets, meaning that you can say that all the order pairs a comma b such that a and b belong to n, right? Which means that n, the Cartesian product of n and n would be, for example, all of these elements like 1 comma 1. Now 1 comma 1 and, for example, 1 comma 2 and 1 comma 3 and so on and so forth all the way up to infinity comma infinity. Now if I this function, this binary operation, so when I write So we said that basically, as a definition, we said that a binary operation star on a set A is a function such that this function is true, right? So then you can say that star is a binary operation on the set A, which means that for example, if this is actually a function, then subtraction is a binary operation on the set N, on the set of natural numbers. But then here the problem is that suppose that I take, for example, so what this means is that if I take any element in the set, in this set, which is the Cartesian product of n and n, and if I call that basically a comma b, that is mapped to a minus b, right? And this a minus b has to belong to n as well, right? Now, if I take, for example, 1 comma 1, then 1 comma 1 is 1 minus 1 is going to be equal to 0, which does not belong to the set of natural numbers. Which means that basically subtraction as a function from n times n, or the Cartesian product of n and n to n, is not a function, which means that basically subtraction is not a binary operation on n, right? On n. A binary operation on the set of natural numbers, which is basically n. So that's basically the meaning of the whole thing. Now let's now the example that we had here was example number 30, which was show that subtraction and division are not binary operations on n, which was basically this question over here. So let's take a look at the solution. Okay, so as the solution here, of course, we are talking about subtraction and division are not binary operations on n, and what that means is that subtraction, of course, is not a binary operation on n, meaning that if you have an ordered set, for example, something like, for example, you have a set of elements like n, the Cartesian product of n and n, and suppose that you have 1 comma 1, then 1 comma 1 would be 0, and 0 does not belong to the set of natural numbers. And by definition, we said that if star is a function from n times n to n, then we say that basically star is a binary operation on n, right? On n, that set of natural numbers. Now, as you can see, I gave you just a counter example that that's not the case. Moreover, basically division, for example, let's say that you divide for example, well, actually you would think that division is a binary operation on n, because, for example, anything that you okay, so for example, suppose that you divide 1 by 20. 1/20 does not belong to the set of natural numbers. Okay, so that's basically the reason. Now let's take a look at the solution, and the solution here is that the basically subtraction as a function from the Cartesian product of n and n to n given by a comma b give to basically a minus b is not a binary operation, is not a binary operation as the image of 3, 5 as the image of 3, 5 would be 3 minus 5 is equal to negative 2. Under 3, 5, under subtraction, this is actually subtraction, I don't want to confuse you or anything. Under subtraction, so this is subtraction. Under subtraction is 3 minus 5, which is equal to negative 2, which does not belong to n. And similarly you can say that division is, or let me write this over here. So similarly division as a function from n, Cartesian product of n and n to n, given by basically a comma b to a divided by b, is not a binary operation, as the image of 3, 5 under division is basically 3 divided by 5, which is equal to 3/5, which does not belong to n, of course, right? And therefore basically subtraction and division are not binary operations on the set of natural numbers. As another example number 31. Example number 31. So we have show that star basically as a function from R, the Cartesian product of R and R to R, given by given by basically a comma b to a plus 4b squared is a binary operation. Okay, so now since a star as the solution, we can say that, of course, this is a binary operation because any a comma b that you can find in this set R, in this set, the Cartesian product of R and R are two real numbers. You take a real number and add it to another real number raised to the second power times 4, so that is again a real number. Add two real numbers together, you will get a real number, and that real number, of course, belongs to the set of real numbers. So this is a binary operation. Now, as a solution, you can say that since star carries each pair a comma b, carries each pair a comma b to a unique element. Of course, the reasoning that I gave over there was not complete, was not wrong, but it was not complete. Meaning that this star actually has to be a function. That I forgot to say. So, meaning that under star, basically every element of the Cartesian product of R and R has to have a distinct image in R. That has to be the case, of course. So since the star carries each pair a comma b to a unique element, a plus 4 times b squared in R, then star is a binary operation on R. Is a binary operation on R. So that is basically valid reasoning in this case. Now another example. Another example, 210. Okay, so now example number 32. Example number 32, we have let P be a set of all subsets of a given set X. Let P be the set of all subsets of a given set X. Of a given set X. So when P is the set of all subsets, of a given set X, that means that P is the power set of X, of course. That is basically denoted by P of X, and that becomes a set which contains different sets. So over here, the elements are just sets, meaning that, for example, let's say that you have a set. Over here, for example, A, and A is basically the elements of A are 1, 2, and 3. then the power set of A denoted by P of A is the same thing as all the subsets of A, all the possible subsets of A, which is basically, for example, the set containing 1, the set containing 2, the set containing the element 3, then the set containing, for example, 1, 2, then the set containing 1, 3, and the set containing 2, 3. And then, of course, the empty set, and also the set itself. So 1, 2, and 3. So as you can see, I have 1, 2, 3, 4, 5, 6, 7, 8, which is 3 raised to the power 2. So if I take, basically, if I take the number of the elements of A as n of A, which is equal to 3 in this case, then 2 raised to the power 3 is equal to, then basically you can say that, if I call this, for example, some lowercase p, then 2 raised to the power p gives basically the number of all possible subsets of A, right? And what that means is that, so of course this happens to be, since the power set of A is basically a set that contains all the possible subsets of A, then that means that then, of course, this number 2 raised to the power p is going to be equal to, is going to also be equal to the number of elements of the power set of A, which is the same thing as n of p of A, right? Which is the same thing as n of p of A, which means that then basically so when we say here that P is the set of all subsets of A, is the set that contains all the subsets of a given set X, then that means that P is basically the power set of X, right? Now, so now let's see what the question is. Show that the union as a function from P to P, you want to show that union as a function from P times P to P, meaning that union as a binary operation on the set P given by A comma B to A union B, and intersection as a function on P, as a binary operation on P given by A comma B, basically gives A intersection B are binary operations on the set P. Are binary operations on the set P. Okay, so now what this question is asking, it's saying that P is the set of all subsets of a given set X, for example. Let's say that, for example, a given X, you have A, and A has 1, 2, and 3, and basically all the subsets of A would be basically, for example, 1 and 2 and 3 and 1 comma 2 and 1 comma 3 and 2 comma 3 and basically the null set and also the set itself. So since that is the case, now we have 1, 2, 3, 4, 5, 6, 7, 8 sets here, which is basically 2 raised to the power 3, which is equal to the number of the subsets of this set. Now, basically the set P in this example is going to be a set containing all of these sets. Meaning that you have a set over here that contains 1 and 2 and 2 and 3 and, for example, 1 comma 2, for example, 1 comma 3, for example, 2 comma 3, the empty set, and the set containing 1, 2, 3. So that is basically P. Now, P is basically this set containing all of these sets, and the Cartesian product of P would be basically all the relations from this self back to itself, meaning that you will get basically a set that contains all of these ordered pairs of, for example, 1 comma 2. So for example, let's say that you have all of these elements in P, and then again you have P over here, and P times P, or the Cartesian product of P and P, would be all of these elements listed here, and again all of these elements listed here. By element I mean, for example, the set containing 1, the set containing 2, and so on and so forth. And then, for example, the set containing the element 1 and the set containing the element 1, and that will be mapped to this one. And then you have the set containing the element 2, and then again this will be mapped to this one. You have the set containing the element 3, this will be mapped to this one, and so on and so forth. So which means that you have basically all of these ordered pairs, which means that you get all of these ordered pairs as the set containing 1, comma, the set containing, for example, 1. And you will also get basically another ordered pair, for example, the set containing 1 and the set containing 2, and so on and so forth, right? Now, what happens here is that basically this binary operation on P would be, for example, union from which goes from the Cartesian product of P and P to P, meaning that basically A comma B gives you basically the union of, if I'm talking about the union, for example, suppose that I'm talking about the union of P times P to P, then what that means is that A comma B basically goes to A union B. So what that means is that, for example, then any of the elements in the Cartesian product of P and P would be, for example, this ordered pair over here. Exactly this ordered pair over here. And that gives basically, for example, the set 1 union with the set 1, and that is going to be the set 1. And this belongs to, of course, the Cartesian, that belongs to, that does belong to P, because P is basically this set which contains 1, 2, and 3, and so of course 1 belongs to P, right? So this is going to work throughout all of these ordered pairs that you might get here in the Cartesian product of P and P. And also, if I'm talking about the intersection as a binary operation on P, I would have intersection P times P to P, and then I have basically, and this means that basically A comma B means that give to basically A intersection B, which means that if I have the same ordered pair, for example, the set containing 1 comma the set containing 1, that gives me the set containing 1 intersection with the set containing 1, which is the set containing 1, which belongs to P as well, because again P is this set over here and 1 belongs to P as well. So this is going to work all across, intersection and union is going to work all across basically this set, the Cartesian product of P and P. But of course this is I wouldn't take this as a logical proof or anything. I just wanted to explain the example to you. But I suppose the solution hasn't provided a proof either here. Meaning that the solution here is basically, since union operation carries each pair, since the union operation carries each pair, A comma B, in the Cartesian product of P and P, to a unique element. And again, I forgot to mention that, again, whether you're talking about the union or the intersection, this has to be a function. Has to be a function. Otherwise, then you cannot say that, for example, intersection is a binary product on the set P, right? So basically you can say that since union operation carries each pair A comma B in the Cartesian product of P and P to a unique element A union B, A union B. Okay, so then you can say that since union operation carries each pair A comma B in the Cartesian product of P and P to a unique element A union B in P, then basically intersection is a binary operation on P. is a binary operation on P. So, and the reason why that is the case is that basically the union operation carries each pair A comma B in the Cartesian product of P and P to a unique element A union B in P. And so why that is the case is that, for example, suppose that you have the Cartesian product of P and P, and that becomes this set over here. Now, if I take, for example, this ordered pair over here, right? This is going to give me, for example, this is going to give me this set over here. And if I take another basically ordered pair, for example, 1 and 2 here, that is going to give me basically the union of these two, which is going to be a set containing 1 and 2. If I take, for example, another ordered pair, for example, 1 and 3 here, that is going to give me the union of these two, which is going to be basically 1, 3, and so on and so forth. Which means that there is and suppose that, for example, I take 1 with 1, 2, 1, 3. So then the union of these two would be 1 and 2. The union of these two would be 1 and 3. So there is no way that you can get any repeated elements as the image of this function. And as a result of that, you can say that since union operation carries each pair A comma B in the Cartesian product of P and P to a unique element A union B in P, then union is a binary operation on P, right? And then the same applies to intersection as well, meaning that you can say that similarly the intersection operation which basically this is the intersection operation, carries each pair A comma B in the Cartesian product of P and P to a unique element A intersection B in P. Therefore, so similarly, the intersection operation carries each pair A comma B in the Cartesian product of P and P to a unique element A intersection B in P, and so basically, and therefore intersection is a binary operation on P. And therefore intersection is a binary operation on P. Okay, so that was basically question number 32. We have a couple more questions, 33, and we have a couple more definitions, and so on and so forth. We will talk about all of them in the next video. I'll see you in the next video. Thank you.